All right, good afternoon, everybody, and welcome to the SETI Institute and another episode of Spacebook Live. And you know, why be organized and plan ahead when you can be impromptu? Sometimes impromptu is much more fun, and we've got a very special event today because we have, for those of you who follow us on a regular basis, we have a wonderful program called Laser SETI. And we've done Facebook Lives or Spacebook Live episodes about that in the past, and you've met the principal investigator on that, Eliot Gillum, and you're going to see him again today. And this is a program where we are developing and have developed, as you'll see, an optical system to look at the sky 24 hours a day, 7 days a week, all over the planet, and look for technosignatures in the form of laser pulses or short duration, high intensity, probably monochromatic light sources that would certainly be an indication of technology or life, intelligent life beyond Earth. So it's an incredible program, and we're here today and in this impromptu way because we are doing an update for our supporters and donors who've helped make this program come to life. And so Eliot came in today with the hardware, with the first observatory hardware that we're actually going to be deploying, and so we thought, hey, let's share the news and tell everybody out there in our Facebook audience what's going on and give an update. So Eliot, come on over. And Eliot's got the cool Laser SETI t-shirt on, and for $1 million donation, you too can get a Laser SETI shirt. In fact, we'll sign it for $1 million. We'll probably sign a lot of things like this. Anyway, good to see you. And thanks for coming in. So why don't you, I mean, the last time I think we did a Facebook Live, where were we? I think we had like one of the camera housings and sort of walked through the basics of it. Now you've got a complete assembly. Maybe you could tell people a little bit about the assembly, about the project, and where we are and what's next.
Sure. There's a ton of things going on, a ton of work gotten done. Last time people might remember that we had something that looked like this central thing in here. It wouldn't have had this motor-controlled shutter. It had just been the two cameras sitting side by side as we had imagined. But now we've built a full observatory around it, basically.
And it's more than just a couple of cameras.
Absolutely. So you can't really see under here is a PC that does all the data reduction from high-speed data from the cameras. There's a hard drive here for storing all that raw data for as long as we can afford to store it.
Yep.
Data is analyzed in real time, so we don't have to keep it, but in case we want to go back and
So will that like store data in real time as we're also transmitting it through a LAN for real time analysis?
Well, the real time analysis happens on the computer
on
right
the computer.
there.
Okay.
So we can still go back to the footage for an instant replay for some couple weeks, but then the hard drive will run out of space, so we'll just keep recycling, that way. Then we have another computer up here, which if this is the brains, this is kind of the nervous system and the muscles.
Right.
It's got a GPS for a super accurate clock, gyro and accelerometers to measure any vibration in the system, because if you move the top of the camera by 100 microns, then that's 1 pixel on the sky, and
that's like a human hair.
And then we have a camera, so we can see what's happening inside and through the windows of the cover.
Yeah, so this is the outer cover because this is going to be outside in the environment, so you've got to have it sheltered and protected.
Yeah. Yeah, we made the decision that it was better to have it be more robust with these super high quality, basically fancy Pyrex windows, super strong, super clear at all the wavelengths we're looking, rather than to have it open up every night and then potentially have to clean all the dust and stuff that might accumulate. That since we want this to be a long duration, across the world project, we thought it was much easier to wipe a window than to have to clean
optics. And by the way, you mentioned the wavelength. So what is the wavelength range covered by these cameras? How broad are we looking in the optic?
So it's a little bit broader than the human eye.
So it starts at near infrared, or?
Yeah, so the camera has sensitivity from about 400 nanometers to about 1,000, whereas your human eye is more like 450 to 750.
Okay.
So that's blue to red.
Yeah.
Although at the ends we have less sensitivity because that's just how CCDs work.
Sure.
Our peak sensitivity is in the green, just like the human eye.
Okay. So that would be like, a lot of the green laser pointers or argon lasers.
That's why they seem so bright.
Yeah.
You can see up front that's our power with distribution with fuses going to all the different components. Because we have LEDs and we didn't want to drill out the LEDs and then not know if the hard drive was broken, we just created these light baffles so that with the cover on, there's really no way for anything in here to bounce all the way around back into the camera.
Right. So explain the orientation of the camera. So you've got two cameras essentially at a fixed line of sight, although the base is adjustable as you explained to me earlier. And how is it that each observatory is going to be looking at the whole sky? What's the setup idea?
Well, a full observatory would be 4 of these, looking in every 90 degrees, which would cover the sky down to about 30 degrees above the horizon,
Okay.
with some overlap. What we're going to do, instead of building, we have funding for 4 of these. We're going to take 2 and put them here in California,
Yeah.
and have them looking out over the Pacific. And then we want to put 2 in Hawaii and have them looking out back towards California, so that they look at the same part of the sky. And if we have clouds at one site, that way we'll still be looking with the other site.
Okay.
And then most of the time we'll have 2 cameras, actually 8,
Separated
4
by
per field of view.
a couple
so
thousand
that
miles.
If an event happens on the sky, we'll be in a position to triangulate it. I think it's 3 times the distance of the moon.
Yeah.
1 pixel of our ability to triangulate.
Okay.
And that way we'll have super high confidence in any events, and we're much more likely to catch an event.
Right.
Because, for instance, right now in Northern California it's cloudy.
Yeah, which is strange but true.
It's good for the vegetation.
It's good for the vegetation, and we get lots of snowpack. I understand, like 200% in some places. Okay, and the system has an optical grating on it. So explain what the optical grating is doing and how that's helping us determine what we're looking at.
Yeah, so that's right here, sitting right there in front of the lens. This is the camera down here. So the grating is matched to the camera orientation, and what it does is it takes a point source of light and spreads it out. And since a prism, people are familiar with,
it breaks down,
creates
the
one rainbow.
Yeah.
So a grating actually has many sets of refractions, and so we've optimized these gratings to produce 2 spectra from every point source of light.
Okay, and so it would, if you were looking at the actual image, you'd see each point source really spread out like a line.
Yeah.
And that would the left and right ends of that line would be different wavelengths, essentially.
Yeah, stars basically in Morse code look like dash dot dash.
Yeah. Yeah. Interesting.
And then what that allows us to do is that the broad stuff, the dashes, are not what we're looking for.
Right. Yeah.
And the dots are.
Yeah.
And so if we see dots that are far enough apart, not too far, the right amount of where they should be, then that means we got a monochromatic transmission at that wavelength according to the separation at the point in the center of those 2 dots.
Right, right. And we're also able to detect very short duration pulses, right? If there was really like a millisecond type pulse of laser light.
Yeah, the cameras read out a little bit faster than, it's about 1.1 kilohertz. So we get a row of data out of the camera about every 900 microseconds.
Yeah, yeah.
And so that gives us good time resolution. We want to observe whether it's the technosignature pulse that we think might be really short.
Sure.
Of course, it might be an hour long. We don't know.
Yeah.
Fortunately, this thing can actually do both because we have this spectral resolution. We can take all the broadband sources and throw them away. We can now say, oh, well, it showed up for 10 minutes, but it did show up and disappear, and it stayed with the stars on the sky.
Yeah.
And so we can recognize a much wider range of signals because we're not relying purely on the duration.
Okay, all right, interesting. And so, you might ask if you haven't kind of studied this program before, so why look for laser pulses? I mean, this is a SETI program. It's very much like radio SETI, but instead of listening for radio waves, we're looking for optical signals. And why might we do that? Well, we send out optical signals, high-intense laser beams all the time. Our telescopes actually use them as part of the method for doing alignment and focusing. So we're using high-energy lasers for that. They're used in telecommunications, free space lasers for communications, and if you've heard of this program by the Breakthrough Foundation called Starshot, the idea is ultimately to build an array of very high-energy lasers to propel tiny microchips with big mylar type of sails at near light speeds or fractional light speeds off to Alpha Centauri. While that's a program that may be decades in development, the idea is using even lasers, using photon pressure as a means of doing acceleration would be a very visible phenomena. If we took, in fact, up the road here, we have the Lawrence Livermore Labs with the world's highest energy, highest power laser. And if you took that laser and coupled its output into one of our existing 8-meter telescopes, for example, on Earth, and shined it out in the sky, it would outshine the sun by 10,000 times. So looking for laser pulses is, has a lot of merit to it. And this would be really the first SETI program of any kind in any wavelength that would really be all sky all the time, which is, I think, the most exciting thing.
20 years ago, we thought that was going to be the optical.
Right.
And just for a sense of scale, what Breakthrough Starshot is trying to do is send a 1-gram spacecraft to 20% of the speed of light. This system, as set up right now, could detect that launch from a maximum distance of 37 light years.
Yeah.
If you scale that up to a kilogram, then it's 37,000 light years, and you could pick it up literally halfway across the galaxy.
Yeah,
and that's only 1 kilogram.
Yeah, that's amazing. That's amazing. So this is very exciting. So where are we now in terms of getting the first observatory, or getting eyes on the sky and starting to collect data and do some field testing of the system?
So we've been running the system in the lab for 2 months. We think we've got it all dialed in, dashboard, thermal, air, everything is good there. We've got one more battery of tests to run, and as long as nothing significant is found there that we can't quickly adapt to, then knock on wood, we'll be on the sky within the end of the month, probably.
Yeah, well, that's very exciting. We'll certainly be looking for an update then. And talk about some of the other locations that you're considering for putting the observatories in place.
Well, it's dependent on a number of factors.
Sure.
It's definitely a very fun and challenging aspect of the program, because it would be easier to just have things looking straight up, lots of places around the Earth.
Yes.
But then you need that many more. You need an observatory per enclosure. Right. So, the plan I've designed has about 60 of these things spread in about a dozen different places around the world, where you generally need to be near oceans, because we don't have land to look up over the oceans, so we have to look over those, and the Pacific is kind of big. Yep. But you also have to avoid light pollution. Yep. But you also need power and somebody to make sure that the gear doesn't walk away while sitting on the ground somewhere. So ideally, it's something like California, Japan, Central Asia, someplace maybe Eastern Mediterranean, and then maybe the Canaries isn't, there's already a bunch of observatories there. Right. Qualitatively, going to a place that's already an observatory
makes a lot of
is great.
Easier. Yeah.
But then you have to set up the relationship with the observatory, and if there's funding that needs to happen, versus if we found another suitable site of a private nature, then that could be fine. Yeah. If somebody came in with a big check to deploy the system today
in their place,
then maybe we'd go.
Well, we've got people coming in from Brazil, from Kurdistan, from Chile, from the UK. Great. So if you're out there and you have a location you think would be suitable for one of our observatories that meet some of the criteria Eliot mentioned, of maybe being close to the ocean, dark sky, having access to power, etc., let us know. And if you want to fund it, even better. But and you were talk about your trip out to was it Bhutan, right?
Yeah.
Yeah, that was pretty interesting.
That was pretty amazing. I mean, it was much more of a personal nature in that we were looking around the country for possible sites.
Yes. You were the guest. I mean, it was basically the king that had you and Pete Warden, I guess, and others as guests, because they're interested in building observatories and promoting science in the country.
As a way to promote general interest in technology and information technology, the way of the future.
Yeah, fantastic.
And it was an amazing experience. That's a really neat country, wonderful people. I really enjoyed it.
Yeah, that's amazing. And it was quite a journey just to even get there, I guess.
Yeah, and I've never met a king before.
Right.
And it's weird as this normal guy when you walk around and people realize that you're a guest of the king, walking around in this country that reveres their king, who just instituted democracy, but they still revere this guy. And
so you didn't have any problem with people buying you drinks then? That's pretty cool. I've never met a king. I don't know. Lee, have you ever met a king?
Plenty.
Well, Lee, he gets around.
5 or 6.
Yeah, 5 or 6. Anyway, that's very cool. So just quickly, back to kind of locations, we've got folks watching us from Buenos Aires and from Michigan, from New Brunswick in Canada, from Arizona, from Sacramento, Mobile, Alabama, from Brazil, from Kurdistan, from Chile, from the UK, Lexington, Kentucky, Fresno, Phoenix, Arizona, Lancashire, England, and looks like Conroe, Texas, and in France. We usually have somebody from Christianland in Norway. I don't know if you're on. Let us know because you're usually there. So say hello. We've got a question coming in here for you that says, "Have you tried to use the Apollo mission laser reflectors located on the moon?" This is from somebody from Trevor. That's an interesting question. I mean, you'd have to shine the laser at the moon and then see if you could see it with this, but it's a good question.
Yeah, no, we don't have a laser to shine out. We're only the receive part of that system.
Yeah.
If somebody were to shine a laser and try to bounce it off, then that could be interesting. I'd have to do the math, but I think if we got the timing right, a sufficiently powerful enough laser, certainly be more than a laser pointer. It'd probably be something the size of this desk. If we got the timing and the pointing exactly right, that'd probably be the hardest thing.
Well, if I understand correctly, the Apollo 11 mission, one of the things that Neil Armstrong did was deploy a retroreflector. And the laser that they shined at it was at the Lick Observatory. I don't know if it's still there, but it means as well that the retroreflector is aligned with the Lick Observatory. And that was actually the results of doing that enabled the first very precise Earth-Moon distance measurements. And as a result of actually being able to shine a laser onto the moon and reflect back, we were able to, for the first time, to actually verify what up till then had been just theoretical, and that is plate tectonics, the fact that the plates on the Earth's surface move.
Interesting.
That was the first time we were actually able to
We could have done it with GPS, but we didn't because
we didn't have GPS at that time. So this is 69. So
well, the other problem with that would probably be that the moon is very bright.
Yeah, that's true.
If the retroreflector were floating in space, I'm confident we could do it with the timing. But you put it on the moon, and that's the brightest object in the night sky, and we might just be blinded by all the other broadband.
Well, interesting question.
It's a good thought experiment to see maybe there's a way we could do it. Maybe with a new moon,
for example.
Then
if I'd have to with the mirrors.
If at full moon, these things are going to be blinded, and I'm confident we're not going to pick up a laser.
Okay.
But maybe with a new moon. Maybe I'll run some numbers.
Yeah, all right.
Good idea.
Can you put one on the dark side of the moon?
Actually, I had previously thought we could just put them in space. Just like Kepler and TESS.
Sure.
The issue there is just you'd be building a different observatory to go around the cameras.
Right.
And you'd have station keeping and all of those sorts of things. So, again, it's kind of a question of if somebody funded the $5 million to build the one on the Earth, and they still had $1 million left over, I'd say, great, let's put a couple in orbit and see what, you lose about 1 magnitude from absorption in the Earth's atmosphere. We everything is just brighter up there.
It would just take you further out, essentially, in terms of sensitivity.
Yeah,
interesting idea. Well, and as you know, if you're a regular follower of space stuff and news, China has landed hardware on the dark side of the moon. That was just a few months back, I guess. So the Chinese have landed on the dark side of the moon. And it would be interesting, and we talk about that. It would be a great place to put a radio telescope as well as an optical SETI instrument. So in any case, you're looking to get deployed in about a month and collect some data, and we'll be in a nice position at that time to do an update, show everybody. I don't know, Lee, if you can, go ahead.
That'll be when we turn on the cameras.
Yeah, right.
We have data from a camera on the sky.
Okay.
That's how we decided to build the instrument in the first place, is to make sure that everything looked right in the first place. What's going to be really interesting is when we get both cameras simultaneously running for a long period of time and start to match everything up and see how do the statistics compare. Because of the noise in the sky, the noise in the optics, and in the camera, there's little things that happen. And occasionally they can fool us, and that's why we have two cameras, is because...
So it's really part of the false positive mitigation.
What we need is weeks or months of that data in order to make sure that the false positives really aren't happening, and start to see if there's real phenomena out there to be observed. We have some ideas of what we might see, but obviously with technosignatures we're extrapolating from a data set of 0, so who knows how long we'll have to run before we find that.
Yeah, very cool, very interesting. And are the two cameras looking at the exact same field of view? They are,
They just look at it, one reads out this way and one reads out this way.
Also, the gratings are orthogonal to each other. Okay.
And the CCDs.
And the CCDs. Okay, interesting. All right, Lee, maybe if you can come around back, I just want to show folks the back because I think this is kind of fun. You know, we're normally, and this weighs, I think the answer is about 200 pounds because of how solid and robust the stainless steel base is for this, and so it's very rigid, designed to maintain a very still alignment. I guess here are the screw mounts you said that give the whole box, if you will, the ability for 7-degree incremental changes in elevation. And these are the exhaust pipes because we've got a big V8 engine in there. No, we really don't. But this is pretty cool looking on the back end. And you did a lot of the design, or pretty much all the design of these hardware elements, which were done with 3D printing. Mm-hmm. In some cases, your own 3D printer. In other cases, you had to farm it out for different material technologies. But all of that is your own design work.
Yeah. I code up the objects the same way that actually my family writes code, and they've done some 3D printing too.
Is that right?
Yeah. The family that codes together stays together.
There's the truth.
So you can build an object like this in an hour or two.
Yeah.
Something more complex like this is a bunch of shapes. It's often hard to see when you look at an object how it was made. Yes. But then once you start turning some stuff on and off in the computer, then you see, oh, I get it. That's just that, and this is that. Right. Yeah, it's a very quick way to be able to say, great, I need something that holds it exactly like this. Get some cool sculpting up here so that we have airflow channels. We have a custom fan mount, and the airflow channels take the air right where it needs to go. Right. So we get the maximum cooling efficiency rather than having to have a larger, more disturbing airflow. Well, what you've become involved in, as a result of this project, is not only understanding an optical instrument, an electronic instrument, a digital data instrument, but how you build things to be robust and autonomous in harsh environmental conditions. I mean, it's a whole different engineering problem, right? Yeah. This thing is designed to tolerate fairly. So we want it to be able to observe in windy conditions, because if you go to an observatory, it's likely to be on a mountain. Yes. And 50-mile-an-hour winds are far more common up there than they are for most of us. Yeah. And so I wouldn't want to miss 10-20% of our observing time, maybe even more, because we were shaking because of the high winds. Right. But you get to 100-mile-an-hour winds and hailstorms and stuff like that, then that's more about it doesn't happen very often, and we just have to weather the storm
and make sure it survives.
Yeah. I feel good about both of those things. Hurricane kind of stuff, I'm not sure whether I'm pretty sure you got a 3-inch branch coming at those 6mm Pyrex windows, and you might actually do some damage. But I mean, just water, and snow, just rain, and things like that. You've got to make sure it's waterproof, and it's one thing to just make something waterproof for a little while, but something that sits outside all the time, and you've got delicate equipment inside. Waterproofing it is not trivial. Yeah, just this gasket here, this double-layer gasket, was a good probably 3 weeks of trying different materials in order to. Because you can't just go to Home Depot and buy any old thing. It's right. Crack or break or that sort of stuff. And so have to find the right materials, and you have to get them and try them and then test them. Yeah. So you're right. It's definitely a lot going on here. Yeah. Just this little orange piece is for this camera to be able to know where the shutter is. And we've got a computer vision algorithm that can tell where the shutter is, even though from the camera's position, the shutter can be in lots of positions that are hard to tell from there. Yes. But by counting teeth with the computer vision algorithm, we know where the shutter is no matter what it's doing. Wow. And this is just a contrast pattern. So there's quite a lot of compute actually in the system as well. There's a lot of hidden details. Yeah. And by the way, what's the data generation? How much data will this generate per unit time? So each camera is about 200 megabits of data. And so the PC processes that in real time, throws it to the disk sort of after it's thought about it. Yeah. But mostly the data that is reduced from that is almost infinitely smaller. Yeah. Because most of the stuff is not an event we think we care about. So you're actually processing data in real time. So you're only really storing phenomena that you think is interesting. That was the only way, because otherwise the storage for that much data would dwarf the cost of the instrument. Yeah, right, exactly. Well, data collection and storage becomes a huge limiting problem more and more nowadays.
And the other question, I guess, that I think is interesting is, what is going to be done with the data? Will people out there, citizen scientists and curious folks, be able to get access to the data and look at it and mess around with it and see what's there?
Yeah, so I think my first goal would be to just have some, a website that explains the instrument and shows example data and some cool events and can teach somebody about the instrument.
Mm-hmm.
It's definitely very easy to put the raw data online, some amount of it.
Right.
Obviously, we're not going to pay for hundreds of terabytes of raw data.
Yeah.
If somebody were to want to work with us and write code that maybe is a better detector or finds a different type of signal or that sort of stuff, then that would be quite interesting, and we'll have ways for people to work with us.
Yeah.
Once we get the system online.
Yeah. Excellent. Well, I think you'll have some takers. Any more questions out there?
No, we have a lot of suggestions for where to put the
Okay.
camera, so I'll
All
share
right.
those with you later.
Yeah. All right. Well, thank you. So we're getting people saying, "Hey, I've got an idea of where to put a camera system," and so we'll look forward to your suggestions. We'll get those compiled and in Eliot's hands so we can take a look at them. So anyway, well, that's the update for Laser SETI, and thank you for joining us and jumping on with this little impromptu session. Hopefully more folks will get a chance to see this later on our Facebook page. And Eliot, thanks again for bringing it in and for updating us and updating the folks out there. It's very cool. We're very excited, and we'll really be looking forward to the next update after we've been on the sky with a dual camera system.
And thank you to everyone out there.
Yeah, well, that's true. I mean, some of these folks, I don't know if any of you participated in the Indiegogo campaign we had to raise money initially for this project, but if you were involved, thank you for your support. There'll be future opportunities because we're going to be raising funds again once we've field tested and we're starting to build and deploy more systems. So if you didn't get a chance earlier, there'll be other opportunities. But again,
I got some more T-shirts.
There's more T-shirts, and like I said, $1 million, I'll send you a T-shirt personally, even for a much smaller amount. But anyway, thanks for watching. Thanks for joining us from the SETI Institute in Mountain View, California. Goodbye for now. Thanks again, Eliot, and we'll see you next time.